select the graph that would best represent the pH solubility curve for this drug. So the first thing you would need to do is to calculate the pKa, right, of the drug. So acid or base, what's the pKa? So this drug is an acid, right? Its parent pKa is 4.8, right? So we don't really have anything pulling that pKa down, right? So our pKa is around 4.8. It's an acid, right? So as you increase the pH, you're increasing the ionization of your acid. So it's going to increase the solubility. So for that reason, both curve A and curve C are out. So we know those are both wrong because they're going the wrong way. So then that brings you back to curve B or curve C. So the second thing you have to do is look at the intrinsic solubility. And here I gave the intrinsic solubility in milligrams per liter. So you would have had to divide that by the molecular weight to get millimoles per liter, which is what this y-axis is showing. So 4.964 divided by the molecular weight gives you 0.02. So that's the baseline of the curve. So you want to look at where the curve increases and then also the baseline of the curve. So for the exam, you might have noticed that maybe your scores were higher than you expected, and because I gave a lot of partial credit. So for this question, curve D is the right answer, but if you picked curve B, you got partial credit, because that means you knew that it was an acid, you knew its pKa, and all that you made a mistake on was calculating the intrinsic solubility. Yeah, so for all of these multiple choice questions in general, I designed them so that I would be able to tell if you made a mistake in calculating pKa or if you made a mistake doing the calculation, and I didn't want to take full credit away if you just made part of the mistake. So that's why some of the answers you got partial credit for a lot of answers, because I could tell that maybe you just made a mistake on the pKa, but you knew how to use the equation, so you got credit for that as well. So for this question, a lot of people chose 6% ionized for this one. So this one, you're calculating the percent ionization of this drug as pH of 5. So when you calculate the pKa of this, you're looking at the carboxylic acid, right? It's an acid. Parent pKa is 4.8, and you're subtracting the effect of this ring structure. That's one carbon away. So right, for carboxylic acid, this is carbon 1 carbon, so that would be -1. And then you go through, oh, go ahead. No, so if it was attached directly to the ring, it would have been 0.75, but there's a carbon between it, so it's subtracting 1. So if you do that and you plug it into Henderson-Hasselbalch using the right equation, the one that you solve for A- over HA, and you solve for A-, right, because you're looking for the ionized form of the drug, this is the answer you get. You get 94% ionized. If you solve for HA instead of A-, you get 6% ionized. If you miscalculated this pKa and just used the parent pKa, 1.8, you get 62% ionized. And 99, I don't know what that is. It's just like, yeah.
I think it's when you assume that the ring gets attached next to it and you use 0.75. You subtract 0.75 if you assume that it's not one carbon away, it's just, attached to the ring. That's why you subtract 0.75. That's how you ended up with 99.
Yeah.
That's what we assumed. That's what I assumed. I didn't assume that there is a carbon in between. I just assumed that it's next to the ring. It's attached to the ring. So once you subtract 0.75, you ended up with 99.
Okay. So I just wanted to point out for the 6% ionized answer though, I want to remind you that when you have your pH, right, pH and pKa, at pH equals pKa, it's always 50% ionized, no matter what. Acid, base, pH equals pKa is 50% ionized. I'm going to ask you guys that on the exam, and you better all get it right. It's 50% ionized. So for an acid, when you increase pH, right, you're increasing the amount of ionization. So you go to a higher pH for an acid, you're increasing ionization. So no matter what, the answer should be over 50%, right? So for this example, even if you miscalculated the pKa and got it too low, you should, the pH is above the
subtracted
pKa,
0.75.
right? So the number, whatever the answer
Oh,
is, should have
yeah.
always been above 50%. So 6% ionized should stand out as kind of an outlier or a wrong answer because it's below 50%. So just keep that in mind always. So for an acid, if it's something above the pKa, it's going to be over 50%. For a base, it's the opposite, right? So for a base, pH equals pKa, it's still 50% ionized. And when you decrease the pH, you're increasing ionization. So it's going to be over 50%. On the other hand, if you increase, it's going to be below 50%. So that's just a way to know how to rule out some of the answers, right? So you should have just immediately got rid of 6%. And if you got that as an answer, you know that you made a mistake somewhere in the calculation. And the other thing that you do too, when you're calculating percent ionization, whatever answer you get, you should go back and plug it back into the Henderson-Hasselbalch equation. So for this example, you just plug this back in, and you know your pH equals pKa plus A minus. So this would be 94% on top over 6% on the bottom. And you should get the right pH. So that's a way to double check your answer. Whatever you got, you can just plug it right back into the Henderson-Hasselbalch equation. So that's question 2. Go ahead. Yeah, so if you got 6% ionized, that means that you you solve for HA instead of A minus somewhere in the step. So on Monday, remember Monday we're just going to have a total review session. We're not going to do any more material, so we'll go through a few more percent ionization problems because I can tell that this one was a tough one for a lot of people. So we'll go through some more examples.
In half an hour batch.
So that's number 2. So number 3, the question is, given the structure below, what would you expect to be the most significant routes of degradation? So the first thing you should see is this group here, right? Esters, amides, hydrolyze. That should just be burned into your brain. Esters and amides are going to hydrolyze. So that immediately should rule out C and D as answers because we know hydrolysis is one of the routes of degradation. So then what you're left with are oxidation versus photodegradation. So photodegradation, remember, are double bonds, right? So you see double bonds here. So B is the answer, photodegradation. Oxidation, you're looking for phenols, right? Benzene ring attached to an OH. You're looking for aromatic amines. So amines that are nitrogen that are in an aromatic ring. Or for tertiary, you're looking for tertiary amines, or you're looking for a sulfur group somewhere, right? You don't see any of those in this structure. So oxidation, you could have also just ruled out oxidation in A, C, and D, and then picked B as the right answer. So question 4 is select the pH log E curve. So for this question, you need to look at the tertiary amine, right? So you have an amine here, which is a base. So calculating the pKa of that, you have 1 electron withdrawing group over here, and you have another one over here. Okay, so you can estimate the pKa of around 9.1 for those 2 groups. And the answer is curve C, right? So you have the log E curves, the pKa aligns with where these curves start to decrease. So your estimated pKa should be right here where it starts to drop. This should have been immediately wrong because they also should plateau at your log P. So this plateau is too high, so that one's incorrect. This one's going the wrong way. A lot of people chose D, which I can understand because you picked where it starts to increase instead of where it starts to decrease, and you got partial credit if you picked curve D. Question 5 is looking just at oxidation. So remember oxidation, we're looking at phenol rings, we're looking at aromatic amines, tertiary amines, or sulfur, right? And sulfur, this form here is already oxidized. So just keep in mind, this is already oxidized. So for when you're looking at sulfur, you're looking at a thioether, so that's just the sulfur connected to 2 carbons or you're looking at just an SH, a sulfhydryl group. So for this answer, you can see that this drug has a tertiary amine, so that might oxidize. You can see that this drug has a lot of aromatic amines, so that might oxidize. And then this one was the one that some people might have struggled with, because you do have a phenol ring. People might have worried, like if you have these halogens, does it still count as oxidation? But you wouldn't have gotten a wrong answer because, you know, once you recognize that both of these oxidize, this is in the question, right? So A is the right answer. If you picked this one, you were missing these aromatic amines as being susceptible to oxidation. Naproxen doesn't have anything that should oxidize, right? You don't have any phenols, you don't have any aromatic amines or tertiary amines, no sulfur groups. So this is the one that shouldn't oxidize, and then these three should. This question is just a definition. So what is the ratio of solubility of your unionized neutral form of the drug in oil versus water is defined as its log P. So your distribution coefficient, or log D, is when you take into account ionization, right? And that's why you get those log D pH curves. So for log D, you're looking at the solubility of both the ionized and unionized forms of the drug. Intrinsic solubility, you're looking at the water solubility of the unionized neutral drug. And then, of course, your dissociation constant is your pKa, right? So, question 7 was asking about the pH rate profile or the hydrolysis. So out of all of these curves, right, remember hydrolysis, you're looking at acid-base catalyzed reactions. So it should be the V-shaped curves. So these two curves, this one isn't showing you the acid catalyzed hydrolysis. This curve isn't showing you the base catalyzed hydrolysis, right? So it has to be one of these two. And then remember, the hydrolysis curves are always centered around a pH of 4 to 6, right? So that rules out curve C. Is this all making sense so far? Anyone have questions? It's easier when you see the answers, though. And the last question, this one confused a lot of people. I think I got a lot of different answers for this question. It's really that equation that we're looking at, the total solubility and intrinsic solubility, right? And I think maybe the way it was phrased might have been confusing. So this one I was asking what's the best statement regarding the solubility in an aqueous solution at this concentration. So ST is your 0.8, right? And SO is given here as 0.1. If you estimate the pKa of this, right, the pKa, you have 2 electron withdrawing groups, each at a 3-carbon distance. So 1, 2, 3 carbons. You have this group here, and then this group over here. So when you plug all of those into that equation 6 and solve for pH, you should have gotten a pH of 8.75, right? And then you have to remember, which way does the curve go for acids and bases, right? This is a basic drug, so it should be more soluble as you decrease the pH. So as you decrease pH, you're increasing the ionization. So the solubility then would fall at the curves of 8.75 and below. So some answers, if you got that it would be soluble at 9.75 and below, that means that you didn't account for these electron withdrawing groups. So you just used the parent pKa of an amine, 10.6, and you got the answer as 9.75. And in those cases, you got partial credit. Because that means you used the equation right, but you just made a mistake in calculating pKa. Answer C is if this was an acid. So that would mean you thought this was an acidic drug, you used the pKa, but then you went the wrong way for the solubility curve. So, and then the answer here just doesn't make sense. It shouldn't be soluble at any pH, right? Because it's over the intrinsic solubility.